So, we are looking at a particular approach to solving the exact equations, velocity potential equations for supersonic flow. It is possible in the case of supersonic flow because the nature of equations is hyperbolic. There is a particular method known as method of characteristics which can be used to solve hyperbolic equations, and the last class we saw how method of characteristics is applied to the 2D velocity potential equation in supersonic flow, and the sum total of what was done in the last class was that if you consider any point, any general point in the flow field at any x and y having a certain Mach number, pressure, temperature, so it is an isentropic flow, you find that it has a certain direction, that is it has a certain direction having an angle theta. There are two characteristics associated with this particular point. One is C plus characteristic, which happens at tan of theta plus nu, that is this is the slope of that particular characteristic. Along the C plus characteristic there is a compatibility condition which is theta minus nu, which is the Prandtl-Meyer angle nu of m, that is a constant along this characteristic curve. Similarly, if you take the C minus characteristics, which happens at theta minus mu, where mu is the Mach angle, then along the C minus characteristics there is another constant k minus, which is theta plus nu, which is a Prandtl-Meyer angle. So, now you have two sets of equations. One is equations for the slope at that particular point, which is C minus and C plus, then the compatibility conditions for those corresponding characteristic curves. This gives us a method to solve the supersonic flow field, and this is similar to or this kind of approaches fall in the domain of computational fluid dynamics, which is CFD, where we are solving for the entire flow field and we get in the entire flow field all values of Mach number, pressure, temperature, and so on. If you happen to have done some CFD, the normal approach nowadays is that you already have a mesh available for a certain geometry, and then the flow equations are solved over that particular mesh. But in this particular context, in the method of characteristics, you solve both the mesh as well as the flow solution marching from an initial condition. So, forward marching from an initial condition. So, you solve the mesh, in this case that kind of a mesh is known as a characteristic net, the mesh as well as the flow conditions at each point. You start from an initial line or initial condition. So, in order to do this, there are certain set of procedures that has to be done for certain points within the flow or at the boundaries. So, what are these processes? We will see. They are called the unit process. If you consider an interior point, that means it is well inside the flow, all its neighbors around it are flow points, they are all inside the domain of the flow. Then how do we solve the equations? How do we get Mach number and the location of this particular point? So, let us take 2 points which we know, point 1 and 2. We know the values, say m1 theta 1 and m2 theta 2, these are known to us already. Then our interest is to find what is m3 theta 3. If you know m3, if you know m1, you also know the Prandtl-Meyer angle nu 1 and you also know nu 2. So, we are interested to find M3 theta 3. What is M3 theta 3? How do we do that? We take the characteristics, corresponding characteristics. So, point 3 is found by the intersection of two characteristics. It is an intersection of the C plus characteristic from point 2 and C minus characteristic from point 1. So, along C minus characteristic, K minus is constant. So, we can write theta 3 minus nu 3 is equal to theta 2 minus. So, along C minus it is theta 3 plus nu 3 plus theta 1 plus nu 1 equal to constant, which is a K minus. Okay. The first equation is for the C plus characteristics, which is theta 3 minus nu 3 is equal to theta 2 minus nu 2. So, use the corresponding equations. From here it is easy to calculate theta 3, it is just K 1 minus which can be evaluated since we already know the values at point 1 and 2. Say K 1 minus plus K 2 plus by 2, and nu 3 is K 1 minus minus K 2 plus by 2. So, we can solve for theta 3 and nu 3. If you get the Prandtl-Meyer angle nu 3, you can invert this, you can look at the charts and invert them, or use a calculator, you can get M3. So, you have solved for the Mach number at that point, and you also have solved for the direction theta 3. So, you know both Mach number and direction at point 3, but where is this point 3 located? So, this point is a location of intersection of two curves, each of them starting from 1 and 2 respectively. Now, in general the characteristics they are not straight lines, but if you take a good number of discretized points which are close to each other, then we can assume that they are almost a straight line in between the points 1 and 3 and 2 and 3 respectively. Okay. So, and also to sort of give a better accuracy, the angle that is taken as an average. So, we know that the equation for C2 plus is actually the dy by dx is tan of theta plus mu, which is Mach angle. So, we take the averages of angles at 3 and 2. It is a sort of, you can use a predictor corrector method where you have an initial estimate of what should be, you can use an initial estimate and then come back and reevaluate also, or just take the averages. So, dy by dx is now a straight line, it is approximated as a straight line. Y3 minus y2 by x3 minus x2 is tan of theta plus mu, where they are average angles. Similarly, y3 minus y1 by x3 minus x1 is tan of the average angles again. Okay. Mu, once you know M3, nu 3, mu 3 can be determined, it is just sin inverse 1 by m 3. Okay. So, you will know mu 3 already. So, it is this is the case for an interior point where it is well within the flow field. Any such point we can solve using this set of equations. You take the compatibility conditions, using the compatibility conditions we can get what is theta 3 and what is Prandtl-Meyer angle at 3. From Prandtl-Meyer angle at 3 we can invert and get Mach number at 3. If you know Mach number, you can get the Mach angle at 3. What we need to know is the location at of 3. Location of 3 is found out by assuming the points that are connected, they are connected by straight lines. This will give us a good solution with the least error if these points are very close to each other, and then you will get you write the equations of the straight line with average angles, and then you can get the solution for x 3 and y 3. So, through this process we get x 3, y 3, m 3, theta 3, nu 3 and mu 3. So, now again at 3 we can define k plus and k minus, and so this process can be taken forward. Now, what happens if we have a point of symmetry? That point 3 actually falls in the symmetry line. It can be, for example, you can take a nozzle of this kind which is exactly symmetric about the center line. Then generally we do not solve for the entire plane because it is symmetric about center line, and we solve only one half of this. So, there is a symmetry line or a line of symmetry. So, when you consider such a line of symmetry, then you will have lines or characteristic lines coming from certain points, and at 3 we find that it is a line of symmetry. So, if you look at a symmetric point, for example, in this case it is symmetric at along x axis, then the angle is 0. So, theta 3 is equal to 0. You can apply this. Then if you take any, for example, you are taking the C minus characteristic which is coming and coming over here, then you know that along C minus characteristic it is nu 3 plus theta 3 is equal to nu 1 plus theta 1, but theta 3 is 0. So, nu 3 is equal to nu 1 plus theta 1. So, now you have got the solution for nu 3, you also know theta 3, and from here you can get m 3 and you get mu 3 also. Okay. So, symmetry point you can appropriately apply a symmetry boundary condition. You have to look at the particular problem. In this case we found that the symmetry was along the x axis, and correspondingly we took theta is equal to 0 at the x axis. Okay. Now, the other case is if these characteristics curves go and meet the wall, that is known as the wall point. Okay. Then we apply the wall boundary condition. It is an inviscid flow. In an inviscid flow, the wall boundary condition is flow is always tangential at the wall. Now, there are two cases usually. If you are analyzing a certain case, then you are looking at a problem where you already know the geometry of the wall, but you are trying to find out what is the flow field. Then what we know is this point 1 is some point within the interior in the flow, and we know a previous wall point. This is a certain section of the wall of the entire wall geometry, and this is a previous wall geometry W1, and 3 is the line which lies on the wall. That is a now this can be a C plus characteristic coming from 1 and impinging on the wall at 3, and what we need to know is what happens at 3. So, since the always the flow has to be parallel to the wall, and if we know the contour of the wall, then we know the angle of the wall at 3. So, we know theta wall basically. So, theta 3 plus nu 3. Okay. So, this is C plus characteristic. So, in a C plus characteristic it is theta 3 minus nu 3 is equal to theta 1 minus nu 1, and theta 3 is equal to theta wall. Therefore, nu 3 is equal to theta wall, okay, theta wall plus nu 1 minus theta 1. Okay. So, appropriately it has to be corrected. Theta 3 minus nu 3 is equal to minus nu 1, yeah. So, this equation needs to be corrected appropriately. So, what we do is put theta 3 equal to theta wall and then solve the equation. But here in general what happens is at point 3 another set of characteristic can be produced, okay, which is now in the C minus direction, C minus characteristic. So, the characteristics, that is a C plus characteristic can get go to 3 and then get reflected from that point. So, but if we are looking to see that we do not get any C minus reflection of these characteristics, this is useful when we are looking to design a contour such that the wall changes in such a way that it will produce always a uniform flow. Okay. So, if you have to do that, then it is possible to do that if the theta wall at 3 is equal to theta 1. Okay. Flow in the neighborhood of the wall, if it is parallel to the wall, already parallel to the wall, then it needs to take no more turn. So, as a consequence there will be no more reflection. This is similar to the wave cancellation that we discussed in the oblique shock case, and Mach waves are nothing but the weak limit of oblique shocks. So, if the angle of wall is such that it matches the flow direction, then there will be no reflection. So, exactly if at point 3 theta 1 is equal to the theta wall at point 3, then there is no wave cancellation. This method is used in order to produce very smooth contoured surfaces for supersonic nozzles. Otherwise, in general, if we look at the wall point, we should see whether there is a reflection or not. So, now let us look at how this procedure is applied, and this is applied extensively for the case of design of supersonic nozzles for particularly contoured supersonic nozzles. If you take as any arbitrary shaped supersonic nozzle, this is a convergent divergent nozzle, the subsonic portion is generally made smooth. Then you have the throat, and we know from our previous discussion on nozzles that Mach number of 1 is achieved at the throat. Okay. After that you have a divergent section to accelerate to supersonic velocities. Now, if you take any arbitrary divergent passage, then we have now just had the discussions that if you have, so what initially it does is that you get expansions. Okay. So, expansions produces a set of Mach waves. These Mach waves get go and hit the wall, and if it is any arbitrary contour, then they will reflect off the wall, and then they keep reflecting off the walls everywhere. Okay. This is considering a line of symmetry. So, in that case, so at every point, if you see here, at every point you have some different Mach number and so on, but what we require in certain cases, specifically for say wind tunnel applications, you need a uniform flow coming out of your supersonic nozzle, so that we are sure that we are giving a specific correct flow or wind to the model which is placed inside the test section. Then non-uniform flows are not possible, or you should not apply a non-uniform flow. If you take just a sort of conical or a wedge shaped nozzle, it will always give a non-uniform flow, because now we can understand what is happening to the flow field within the nozzle. So, then we look at how we can design such nozzles. so that we always get uniform flow at the exit of the nozzle. Now, this based on the principle just we have discussed now on the characteristics and wave cancellations. At the throat there is an expansion, you can have a smooth expansion, then you have for these nozzles you have a expansion section where the flow is smoothly expanded, and here expansion waves are these are nothing but Mach waves, they are produced and they come now and then go and impinge upon the walls. Then in such contoured supersonic nozzles there is a section after the expansion section known as the wave cancellation section, where these Mach waves when they impinge on the wall is designed in such a manner, it is contoured in such a manner that the angle of the flow and the angle of the wall match, and therefore the waves do not reflect again away from this particular point. And once that kind of a contour is achieved, after each such subsequent interaction with the wall, the flow always continues to be uniform with respect to the x direction. So, at the exit you get a uniform flow of constant Mach number. Okay. So, this is done. So, we shall see look at this in a detailed manner for what is known as a minimum length contoured supersonic nozzle. The minimum length is used because if you do look at such contoured nozzles, they are really very long, they have very long extent. They are also used, these principles are also used for design of rocket nozzles also. In such nozzles we do not require long length because it affects the weight of the entire structure. So, it is good if it can be made short, and there the principle used is if this expansion section can be made very sharp, not made so long, but rather it is made to turn at a very sharp corner, then this can be achieved, and that is done by placing a sharp corner, and flow is turned at that sharp corner by a Prandtl-Meyer expansion fan. It is not an extended expansion. So, we will see the design of such a minimum length supersonic nozzle. Then for example, it is given here, it is considered in this particular graph. So, we are only looking at the wave cancellation section. So, all the section over here is only wave cancellation. All the waves are produced at this particular point which is a Prandtl-Meyer expansion. This is also the throat. So, here Mach number is 1 and we are assuming that you have a uniform flow at Mach number equal to 1. So, what should be the initial wall angle so that we get the correct exit velocity at the end of the wave cancellation section. So, that is the problem of how to design these nozzles. If you are say considering that I want to design a Mach 2 nozzle, M exit equal to Mach number 2, then what is the correct angle of expansion that needs to be provided and how the wall should be contoured. Okay. So, we can just take a look at that by looking at these characteristics over here. Okay, we just consider so if you look at the final characteristics that impinges at W2 and trace the way back all the way towards the point 0, then we should be in a position to comment on that particular angle. Now, at the exit we know that the flow is uniform and theta is 0. So, if you consider this particular characteristics, theta is 0 and nu corresponds to Mach number of M exit. Okay, and it is a C plus characteristic. Okay. Now, so this lies along this particular C plus characteristic, but at point 3, but point 3 is also a part of a C minus characteristic originating from point 0. So, along this C minus characteristic you get that theta plus nu is constant, is a constant which is k minus. Okay. So, the expansion is happening through a Prandtl-Meyer expansion, and the angle of turn it gets is at certain value theta. Okay. And if the initial flow is Mach number equal to 1, then we know that nu of Mach number equal to 1 is 0. Therefore, nu that is due to the flow turn of theta should be equal to theta itself. Okay. So, it is equal to theta itself. Okay. Since it is turning, you apply the Prandtl-Meyer equations and it is turning from Mach number equal to 1. So, what we get is theta plus nu, that is equal to 2 nu, okay, 2 nu, and at or 2 this is actually equal to theta plus nu is 2 nu or 2 theta wall, okay, because nu and theta are equal at that for maximum turn, the wall turn that is given over here. So, that is equal to, now from the k plus characteristic it is equal to nu, that is the nu of the exit angle. So, you get 2 theta wall is equal to nu of Mach number at exit. So, therefore, theta wall maximum, the flow turn is nu Mach exit by 2. Okay. So, this is the relationship to find what angle should the wall turn at point 0 in order to get the exact Mach number at the exit. Okay. Now, this flow turn, which is turning by a certain wall angle theta wall maximum, can be divided into several waves, and then each of these waves impinge upon the wall at certain points, and the wall is designed so that it does not reflect any of these, this reflection is not done. Therefore, you get this particular wave cancellation contour. So, if this is correctly done, then we will get uniform Mach 2 flow at the exit of this nozzle. So, we will do a solution for one particular case and see how it can be achieved, and we will also see certain applications how the, once we understand the method of characteristics in supersonic flows, then we should have a better understanding of supersonic flow fields, and we can take a look at that in the next class.